aka Schneems. Jin Tian Tian Shi beads Wo Tian Hao. Wo Jidao Idian Dian Zhengwen. Yeah, that's it. Those, like, if I need to use the bathroom, I'm like, where's the bathroom? And they just kind of point me in the right direction. So on the internet, people call me Schneems. A small fact about me is that I'm very committed to Ruby, so much so I actually married her. This is my wife. Her name is Ruby. Yes, and I met her at a Rails meetup too. This is a crazy thing. She does also program Ruby, but currently she's stressing our relationship a little bit. She has started to program Python. So yeah, I also, it was mentioned, I work for Heroku, and it's really nice. I get to do a bunch of open source with them. You're going to be hearing a little bit about it later. There's a service I guarantee none of you have ever heard of called codetriage.com. That's codetriage.com. Codetriage.com. Codetriage.com is the application designed to get you up and running in open source, and it itself is open source. This is actually one of the apps that I use to play around and test out new things on Heroku, because I get to launch and deploy things for Heroku, and so yeah, they pay for all my hosting. It's pretty sweet. And I've been working on a new application. It's in kind of alpha, sort of beta. If you're not so interested in issues, but you're more interested maybe in documentation, there's a project I have called docsdoctor.org. It's explicitly designed to be as difficult to say as humanly possible. And this will send you one piece of documentation a day. So either a documented method if you're interested in learning more about the documentation, or if you're interested in getting really easy commits, then it will send you an undocumented method. So I've turned this on, and it's like the number of undocumented methods in things like Rails are like almost too great, where it's like too easy for me to get commits. So definitely check that out if you're interested. I'm also an organizer of a conference called Keep Ruby Weird, and I do have a couple of stickers. But what I'm mostly going to be talking today about is one of my contributions to Rails. I'm on the Rails issue team, and I am also recently one of the top 50 Rails contributors. That's it. Okay, I want to talk about algorithms. I do have the title of the talk is Going the Distance, which is a Cake song, and I realize you all might not get the references to the lyrics, so I'm not going to dwell on them too long like I am right now. Okay, so I went to college at Georgia Tech, where I actually studied mechanical engineering. So instead of like writing code and like a button-up shirt and like slacks, I was more more like getting my hands on the engines and Excel spreadsheets. I actually worked at GE designing refrigerators, and instead of multi-million-dollar corporation, we designed refrigerators using Microsoft Excel. That was our programming language. So I've been doing programming for about 8 years now, and one of the reasons I didn't study it in college is computer science was really boring. But programming to me is very interesting. The difference to me is that with programming, it's all about creating things. So I like accomplishing tasks. I'm kind of ADD. I need to see something working. Like, rather than just study the theory, I want to actually play with it. But in all of these years that I've been programming, there's definitely some things that I missed along the way in computer science. And of course, one of them is algorithms. So I'm here to tell you today that algorithms are, in fact, beautiful. So algorithms, they solve a problem, and I had an interesting problem, or I had a problem, which was spelling. So I'm not a very good speller. It's often said, or my parents always said, that it's a really good thing that I went into engineering because I'm such a bad speller. And in programming, it's like, oh, it doesn't matter if you spell the variable wrong, as long as you spell it wrong every time. So as time goes on, you get more tired, you get more distracted, and spelling becomes harder. One of my favorite tools, Git, actually is like, hey, if you try to do git commit, it's like, hey, I know you. Listen, we don't have that here, but we do have this other thing called git commit, and maybe that's what you meant. So I said, okay, that's really neat functionality. I want to add this to one of my own programs. I actually like Rails. So how do they do that? Okay, so in order to do that, we're going to go from mechanical engineering mode to Professor, which one of these is it? Oh, this one. Okay, Professor Computer Science mode. So I would like to introduce to you edge distance. So edge distance is the cost of changing one word to another. And generally, if they cost less, then they're more likely a match. So a really, really super simple example is zat is not a word that I know of, but bat is. How many changes would it take to change zat into bat? Well, one, you can just substitute the z for a b. Okay, that's pretty simple. Or zzat, the cost would be 2 because you can substitute one and then delete one. And, well, it's pretty simple to rationalize about. It's actually relatively difficult to program. All right. First, I wanted to just take a raw stab at it. I was like, okay, I can probably do this. I'm a pretty smart guy. I'm not even going to Google the first time. And so, so I went about it, and my first attempt was this. It's pretty simple. It's only a couple of lines long, and basically all we're doing is iterating through each of the characters and checking and seeing, do they match, which is pretty, makes sense. And if we put zat and bat into it, it says, okay, the distance between these two is 1, which is great. Done. End of talk. All right. But, okay, I played around with it a little bit more, and I was like, hey, let's change Saturday to Sunday. Those two words are pretty similar. What would we get? Well, my algorithm said it would take 7 different changes to get from Saturday to Sunday. And, there's no way. Yeah, that's as long as one of those words is. So it turns out that that algorithm was missing something. But accidentally, in the process, I rewrote Hamming distance. So Hamming distance is also something called signal distance. I found this up by reading a Wikipedia page after I wrote it, which was great. It's not exactly the same because Hamming distance, you have to have the exact same length of string each time, or it raises an error. And it turns out Hamming's really cool. It lets you, it measures the error between two strings. And it's really good for doing things like telecommunication and anytime you've connected to the internet or sent ones and zeros across a line somewhere, you've used or touched the Hamming distance in order to do error correction on those communications. It's really bad for spelling, though. Really bad. Before, it told us 7 to change those two together, and that's not correct. The reason why is Hamming does not include either insertion or deletion. So to do those, I was kind of like, all right, I have no idea how to do this, and I finally broke down and opened up Wikipedia, and I found an algorithm, of course, and it's called Levenshtein distance. Want to kind of go through it. If we look at deletion, we can look at 2 strings that are very similar, but obviously we're supposed to delete the first character. We can see here that taking off the first character on the second string results in a match. So if you were going to code this, you would just basically compare the two strings and not look at the first one on the second string. So that's how we know, okay, hey, we've got a deletion here. For insertion, we do something really, really similar, except instead of the second string, we take a look at the first string. And here it is again. You can see that if we take off the first character of the first string, it matches the second string. This will be true. And then the third operation, which is substitution, is going to be a little bit different from the other ones. We basically want to just say, all right, the rest of the string matches except for these two characters. So in that scenario, we can compare everything on the first string except for the first character and everything on the second string except for the first character. With all of this wrapped up together, imagine that we already have a way to calculate distance. It just already exists. We could find the distance of using this in a recursive method. So one thing to start off our recursive measurement is noting that if we have strings of different lengths, or an empty string to a string will be the length of that string. So changing nothing into foo will cost 3, or changing foo into nothing will also cost 3. So we can just easily calculate that. And that translates really easily into code. Just check if the string is empty, and then grab the length of the other one. Once we've done that, we can calculate the distance between substrings. And again, this is with our imagine that this distance measurement method actually works. So we talked before about minus how distance with deletion, insertion, and substitution works, where we just take off the first character of one or the other. And how we're actually going to figure out which operation it is we're going to figure out the cost of all three of them and then take the smallest. So we don't know ahead of time, and the computer doesn't know, so we have to calculate all three of them. And then you'll also notice over here, highlighted in yellow, that I've got a cost of 1, or I've got a plus 1. And why would we do that? That is actually the cost of the operation itself. So the previous L1, L2, L3 is just to determine which one do we take, and then we add the cost. So we pick the cheapest operation, add 1, and we're almost there. If our characters match, then we just chunk off that first string and only compare the rest of the string. So in our case, if we have two things that start with an S, Saturday and Sunday, we would just compare Atterday and Unday, which are not words. Okay, so you put all of this together, and magically it forms a recursive Levenshtein distance. And here's kind of what it looks like. This is exactly the code you saw before, just copied and pasted. We check it if the strings have different lengths. We check if it's a match, and then finally, if it's neither of those, then we go through and we pick which one was the cheapest. If we run this, we see, hey, the distance between Saturday and Sunday is 3, which is like way better, because it turns out that that's actually correct as opposed to the other one, which is not correct. And to give you an idea of what this actually looks like, I took a video. So we're going. Still going. I did add a sleep in here. I'm just a really small one, just to give you a kind of sense of time scale. Okay, this took 1,647 substring comparisons and returned the correct distance of 3. I did want to mention that if you go to github.com/Schneeman/going the distance, all of the code examples and videos I have are actually runnable scripts, so you can feel free to play around with them. So if you get a little bit lost with any of the math, I also put all my notes on there too. So if you get a little bit lost, it's fine. Maybe you can go to it at another time, or even if you have to do some spelling later, you can be like, hey, Schneems did that great distance talk. If only I could remember the URL. Okay, so The first one, which I didn't know was Hamming distance, so I called it dirty distance, took 8 comparisons, was really fast, but it was wrong, so that's not what we want. This one took 1,647 comparisons, but was right. And yeah, there's a song reference in there. Okay, you know, that hurts. That's a lot of comparisons. Can we do better? Is there a better way to do this? And it turns out yes. If you watch that screen, if you kind of blur your eyes a little bit, then you'll notice that the same strings come up on the screen again and again and again and again, about 1,647 times. So if we can calculate the substring string distance and use that to calculate the total distance, we can cache those values, and we end up with the matrix Levenshtein distance algorithm. All right, so to conceptually understand this, we want to start out, how do we convert an empty string to an actual string? So in this case, blank to Saturday. We would go from blank to S is 1, blank to SA is 2, 3, 4, 5, 6, 7, 8. Hopefully that kind of makes sense, just intuitively. And then we want to do the other one. So Sunday to blank would cost, so blank to S would be 1, blank to U would be 2, blank to 3, or you understand. Blank to 3 would be U. No, 3, 4, 5, 6. So it would, to change an empty string into Sunday would take 6 transformations. And if we put these two together, now we have a way for expressing each of the operations that we can make to make those transformations. Okay, so I'm gonna go back to our 3 operations, and we're gonna start out with S. So how much does it cost to change an S into an S? Well, in this case, it's a match, so it's gonna just be 0. If we go to the next one, so S into SA, so the string of S into SA, is going to cost 1 because we need to insert that A. So that's how the matrix is, we're going to be building it. How do we calculate these programmatically, though? Before we had this little handy-dandy cheat sheet where if we cut off the first character of the first string, it turns out, okay, hey, that's an insertion. So we can do exactly the same thing here, where the row index is represented by string 1, and the column index is string 2. So that's the row index, that's the column, that's where we're currently looking at. And then we move the column index over by 1. And so that gives us, this is the value that we're looking at. Basically, if you're going to insert something, you look at the column, or you look at the entry directly to the left of it, and then add 1. So we get 1, and that represents our cost, our total cost of an insertion. If we keep going, we'll notice that all of the rest of these are going to be insertions because it's basically the same as from blank into something else. So that's pretty easy. The next character on our list is SU, and we're going to start over again. We're going to change SU into S. And in this case, we have a deletion because we actually have an S extra character. But we need to be able to programmatically calculate deletion. We did this before previously. We saw this code, and so we can represent it the same way. So we have our column index, we have our row index, and then if you bump it up by 1, this is going to represent the element in our matrix that would refer to a deletion. And then, of course, we add 1 to take care of the cost. So in this case, our cost is also 1. So we've got insertion, we've got deletion. Now we take a look at substitution. You probably kind of get the gist by now. So I'm going to just go through that really quick. We move up, we get our element, we add 1, and the cost is then 1. So now we've got all 3 of those. we also have to take care of a match. Now, match is sort of a special case. A good way to think of it, or difficult way to think of it, it's almost as if that character didn't exist. How much would it cost? And then we don't add one because there's no operation. It's not a deletion, an insertion, or a substitution. So changing a blank, this is changing an S to an S because it matches is exactly the same as changing a blank string into a blank string. So that's why we look at that field and then we copy it over. So when you put all of that together, we get this handy dandy algorithm. And it is going to be recursive, or not recursing, it is going to be looping over all of the characters in each of our strings and figuring out the cost for a deletion and insertion and substitution, picking the lowest one, and then actually putting it into our matrix. And if you go onto Wikipedia, this is going to be a little bit different, just because the index starts from 0 instead of starting from 1. But anyway, here's what it looks like. We start out, and we just go, and go, and go. Again, it does run a little faster than this. It's slowed down so you can actually see it. All right. So, okay, it's always, I love getting the right answer, except sometimes when I get the right answer, like the first time, I'm pretty sure my program's broken. So we can see here that the final cost is 3. One of the really, really cool things about this is with having this matrix, we can actually get the cost of all of the substring matches. So if we wanted to get the cost of changing sun to sat, we just go to the n in sun and the t in sat, and it tells us that is only costs 2. And would you say it's better than recursive? It actually only took 48 iterations to do the matrix version of this versus the 1,647 that it took to do the recursive version. So personally, I think that's way better. I do have another link. It's bit.ly/going the distance. It's slightly easier to remember, also because Schneeman is really hard to spell. And because I'm a Rubyist, all of my spaces are underscores always. So, okay, hopefully you're maybe done taking your naps. Maybe you kind of got that, maybe not. You can still play around with the code. I highly recommend it. Instead of just copying and pasting it whenever you need it, be like, hey, how does this thing work? Okay, so my biggest problem in life is that I'm human, and I generally get tired relatively easily. I drink a lot of coffee, but that doesn't help a ton. And machines don't really understand tired too terribly well. I tried explaining to my machine that it was tired and it should be nice to me. It did not work. I think it laughed at me. So one day when I was really tired, I started typing Rails generate migration. Except instead of typing Rails generate migration, I accidentally typed Rails generate migratoon, which is totally a thing that we should have. I don't know what it would do, but naturally I got like a massive error and I was really upset. And I mean, this is totally just how I felt. And when you're really stressed, it's those simple, like, I can't believe I did that. That just, it like hurts your head. So I figured in these types of scenarios, we know what you're trying to do. You're just not doing it quite the right way. There's got to be some way we could do this. And so I thought of Git, and I thought of, hey, that would be great if we just recommended to you the one of the commands that you can use instead. So in a pull request number 15497, I introduced this. So now inside of Rails, whenever you're using a generator, if you misspell one of the generators, then it will actually try to give you a recommendation. So it says maybe you meant migration, and also gives you the prompt for, if that's not correct, to run Rails generate -- help. And so you have the error, it'll compare the commands, find the smallest distance, and this is also really, after I got into this, I was like, oh, this is so cool, who else uses this? And another small product you might have heard of called Google. So I mentioned I'm really bad at spelling. Sometimes I have to Google spelling to figure out how to spell spelling, and Google tells me it's right there. So I looked into this. Peter Norvig has an amazing blog post where he goes into detail over at the very high level how Google does this. And basically, Google reads a ton of real books, and of each of those books, it categorizes words. So it says, oh, hey, somebody wrote this into a book that was published. This must be a real word. And then it counts each of those words. And it figures that the more often that word shows up, the more likely it is an actual real word. So the, and are most definitely real words and probably show up hundreds of thousands of times. Versus supercalifragilisticexpialidocious might be a real word if you watch a lot of Disney, but it's probably not going to be in there at all. So once we have that, we can compare our dictionary to add the input string. So it's actually relatively quick to just run through all of those entries. And we combine those two probabilities together. What's the probability that our dictionary entry is actually a real word, and how difficult was it to change one entry into another entry? And between those two, Google says, hey, I bet you were probably trying to use this word. Now, Google also does something that's really cool that I can't actually do in Rails, which is like, you might not even notice it or realize that you're doing it, but every time I do this, I always click on the link, and Google's like, ha, I got you. This is exactly what you meant, and then they cache that. So you know what? Next time, they don't even have to do all of those calculations again, which is brilliant. So in addition to these measurement distances, covered Hamming, covered Levenstein, there's longest common subsequence distance, there's Manhattan distance, there's tree distance, there's like a ton of distances. I think it was Jerry actually mentioned, he was like, okay, this is really cool, but like, how do you do this in like Asian characters? And I was like, oh, I'm totally gonna look that up. And I found a white paper on how to do spell checking on Asian characters, and it's really hard. It's totally really hard. But this talk is all about algorithms, and I highly recommend if, maybe hopefully, so after the last time I gave this talk, some people were like, hey, how do I learn more about these? I also didn't have a CS background, or some people were like, I did have a CS background, and I just slept through all those classes. How can I learn more about algorithms? So I recommend Wikipedia. Actually has a surprisingly large amount of good stuff. Also, Rosetta Code is pretty amazing. Rosetta Code will take one algorithm and show you how it's written in many multiple languages. Also, if you're trying to learn a different language, it's actually probably not a great way to compare, just because a lot of them are written non-idiomatically. Like the Ruby one was like, I was like, no Rubyist would ever write it that way. So I actually modified it. Or even better yet, give an algorithm talk. Last time I gave this talk, everybody was like, oh, hey, did you know about blah? And I was like, no, I didn't. And then I wrote it down, and then I did a little bit of research, and it's amazing. And now I'm like a much smarter person. So I challenge you to sign up to give a talk on something you don't know about. It's a great way to learn it. And here's your topic. Give a talk on spell checking Chinese characters. There's a white paper online somewhere that I kind of half understand. Okay, yes. And at the end of the day, like, it's not just like, oh, it loops through and it builds a matrix. Like, these are ways of sharing general institutional knowledge. These things have taken decades to refine and build, and we should like, sometimes you get a Stack Overflow post and you just copy and you paste it and you have no idea why it worked. A lot of people use algorithms like that as well, but I recommend that you maybe every once in a while just set aside like a Friday afternoon when you're not deploying, because you don't want production to break, unless there's like some massive shell shock bash bug. And just spend like an hour looking at this and trying to like understand why it works. And then if you think you got it, try to explain it to your coworkers. And if you don't think you have it, then ask your coworkers, and like maybe they have it. Just like, anyway, go out there, explore, have fun, High five. Does anybody have any questions?